Hello and welcome to the Inertia video tutorial. Here we're going to watch a video and ask what seems to be a pretty simple question, and we'll see if we can get to the bottom of it. This is a video I found on YouTube. It's pretty straightforward. The guy over here is going to push a block of dry ice across the table, and that's pretty much it. He's just going to walk back and forth and do it over and over again. So let's watch. So here's the push, and the dry ice floats across the table, and he's going to catch it, and just going to do it again and again. And the question is, what's keeping the dry ice moving here at the center? So we'll watch it again. Right now, what is it that's pushing the dry ice right there? There must be something pushing it because we see it moving to the side. So right, let's go, come on. Right there. What's pushing the dry ice right there? So I'll move back a few frames here. Right here. What's pushing the dry ice to the left? So, well, let's take a look at what our choices are, what the possible answers could be. We've got the table pushing the dry ice. We've got gravity acting on the block. Maybe gravity is pushing the dry ice that way. Maybe the guy is pushing the dry ice that way. So let's look at each one of those one at a time. Let's look at the air too. So let's start with the table. The table is contacting the block, but the table is pushing the block up. So it really wouldn't push the block sideways. So let's go over here. It's got a picture of it over here. This is the block. And at B, we do have a force up on the block from the table. So that force right there is that's going to be the normal force, and that's the table pushing up on the block. But that's not going to cause the block to move sideways because it's an up-down force, and that's not going to push or pull anything sideways. We do happen to have gravity also pulling on the block at that time, and gravity is going to be pulling the block down. So let's mark that with FG. But again, we have the same up-down issue. That's not going to cause any sideways movement of the block. But what about the hand? The guy's hand clearly is pushing the block. So let's look at this force here. Let's start with the hand pushing the block this way. So this is going to be the force from the hand. Let's mark that. Force the hand pushing the block that way. Well, let's watch the video. So the question is the guy's hand, so we'll watch his hand, is his hand pushing the block at the center of the table? Looks like no. We'll watch again from the other direction. So here, well, right there would seem to be a push. Nothing, 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 nothing. There, he makes contact with the block again. So even though the hand seems like that might be what's going on, if he's not touching the block, there's no way the hand can be applying a force. So then the obvious statement is, well, his hand did apply the force, and it's just the continuation of that force. You can't push something unless you're actually touching it, with the exception of things like gravity or electricity. So, but a push from a hand, you have to be in contact for that to work. So we got to rule out the hand. It can't be the hand. So then maybe the air is pushing the block. Well, the block, when the block is, say, here, there's air to the left and there's air to the right. So why would the air be pushing harder one way than the other? If anything, the air would be in the way of the block and be pushing the block backwards, causing the block to not want to go the direction it's going. So it's not the air. So we're running out of things it could be. And if you look, the key is that there's nothing touching the block. Watch it the other way. Here he's touching it. And here, nothing touching the block. So the question is, what's pushing the block? The answer is nothing. There's nothing pushing the block. So I'm going to write that down. Nothing is pushing the block sideways. point B, which means there is no force keeping it in motion. So the block's just moving on its own. This force here doesn't exist, so we'll get rid of it. The block's just moving because it is. It's just moving. That's what inertia is. It's the idea that the block just moves on its own just because it already was moving. There's no reason to stop. Let's look at points A and C in the video. So you watch the video. So over here, the block, look, moving, and it seems to come to a stop when he touches it. And it's going to move across the table. And it's just going to move, I guess, forever unless he stops it. So we have no velocity. Well, let's see if you can push the block. No velocity to some velocity. So if we've gone from 0 velocity to some velocity, we're looking at an acceleration because the velocity has changed. At the other side of the table, the block had velocity and went to 0. So let's say the velocity was 7 and then went to 0. That's a change of 7. That means we're accelerating, because if you're changing your velocity, you're accelerating. So let's bring it back to the center of the table. How about here? So here the block seems to be just steadily moving across the table, and at his hand the block was accelerating. So we can start to make some postulates here. So number 1, no force, we're talking about sideways forces here, equals constant velocity, which could be 0, or at that possibly 0, because we'd have to have a constant velocity of 0. And force equals acceleration. And we saw that in the video. So remember, no force means no force in the direction of motion. There are forces acting on it, but these forces aren't in the way that the block is moving. So the block is moving to the left or right. So no force means constant velocity, could be a constant velocity of nothing. And if there is a force acting on the block, then that block is going to be accelerating, either speeding up in the case of the push or slowing down here when he puts his hand to stop the block. Both are acceleration. Thank you for watching the Inertia video tutorial.